Hi, everybody.
Hello.
Okay. All right. So today's the last class. Anybody have any questions before we get started? Last bit of material. Okay. All right. Okay, so at the end of last class, we discussed the Fourier transform on the short space, and then briefly an extension to L2. And I'd like to leave that extension to L2 as reading from the book. You can see this in the Stein-Shikharchi, the book called Measure and Integration, so the second book, to extend the Fourier transform to L2 functions. Because a priori it's not defined for L2 functions. The idea, as we discussed at the end of the last class, is to understand its properties as isometry of the short space, and then define an extension to L2 by taking appropriate limits. So L2 Fourier transform is a limit of the Fourier transforms of Schwartz functions, which are dense in L2. Okay, but I want to give a few applications of the theory so far. So one, the first application I want to conclude with is the uncertainty principle. And what this means in a mathematical sense. So you've had some homework questions. One homework question is past week, Heisenberg uncertainty principle. A qualitative form of it. So they're precise mathematical statements, but a qualitative mathematical statement is that it's not possible for f hat, say to be a Schwartz function, to be compactly supported for, maybe let me say it like this, for both f and f hat to be compactly supported. So there just does not exist there does not exist a function, Schwartz function, say f that's compactly supported, that has Fourier transform that's also compactly supported. And I gave this as a homework problem. The proof is pretty quick, or the idea for the proof is pretty quick. If it's compactly supported, in, say, the ball of radius r around 0, extend by periodicity, extend f to be a periodic function. So extend f to be periodic on R, say. Let's just say we're working for functions of the line. The same is true in RD, but so d equals 1 proof. Be periodic function on R, and then you can see that f hat, there can only be, let's call this f twiddle. See that f twiddle can only have finitely many non-zero Fourier coefficients. and then hence f is a trig polynomial, which is a contradiction. Because trig polynomials are not compactly supported. Okay, so that's the weakest form of the uncertainty principles. There's no function that's compactly supported that also has compactly supported Fourier transform. A quantitative version. So quantitative version. There are various quantitative versions. So first quantitative version is called Bernstein's lemma, or Bernstein's estimate, or Bernstein's inequality, maybe. Lots of things named after various Bernsteins, but this is Bernstein's inequality. So if f is, say, an L2 function, Rd, such that support of f hat is in the ball centered at 0 of radius r. So to take a function with compactly supported Fourier transform. So its Fourier transform has compact support. Then for any multi-index d alpha, the derivatives of order alpha of f for any multi-index in L2 is less than or equal to 2 pi r to the length of alpha times the norm of f in L2. So you can bound the L2 norm of the derivatives of f by the L2 norm of f itself up to this factor coming from the support of its Fourier transform. So this is Bernstein's inequality, and the heuristic, and you can sketch this out for yourselves. To see that the same, you might be looking at this inequality and wondering, what does this have to do? I see how this, how is this a quantitative version of this statement? Well, the heuristic is as follows: if f if f concentrates on scales much smaller than 1 over r, then the left-hand side should be much larger than r to the minus much larger than r to the alpha. Did I get this right? Yeah, I think I've got this right. So to check this heuristic, imagine if f has L2 norm equals 1. So support of f hat is in the ball of radius r. So I've confused f hat and f in my notes. So let me write it like this: f hat is ball of radius r. So f hat is like f hat of c. We can imagine is like. So we know that f and f hat have the same L2 norm, right, by Plancherel. So f hat is like 1 over let's do d equals 1 here again. L2 normalized bump. So it's like chi, where chi is, say, just a smooth bump on the ball of radius r, or absolute x, say, over r, and then f of x is like say 1 over r to the 1/2, and I'll put these in quotes. Since it's not possible, we know by the heuristic above. But just for the purpose of the heuristic, to relate this with the previous version of the qualitative version, supposes that both of these guys are kind of bumps, just compactly supported. F of x is 1 over r to the 1/2 times chi absolute x over r. And then you can just see that you get a contradiction. If r times r is much less than 1. Okay, just compute the L2 norms of, so on the one hand, take derivatives of f and compute its L2 norm. On the other hand, take, and then the other hand, yeah. You can just compute the norms, relevant norms in a couple different ways. Okay, so.
Excuse me.
Yeah.
Can you just clarify these characteristic functions?
So what is chi? So for chi, say chi1, chi2, chi 1 or 2 is, say, a bump supported in ball of radius 2, say chi looks like this. Something like this. Here's a graph of chi.
Cool.
So yeah, it's this is just I'm being very imprecise here. So just for the sake of this is what I mean to do here is to say to try to put this inequality and make sense of it in the same universe as this type of statement, which is commonly thought of a form of uncertainty principle. And I'm claiming that this is a quantitative version of that. It's a bit hard to see just from like an inequality that you're exposed to the first time what this has to do with this statement. And so I would just say, like, test out this inequality. You can see this inequality obviously fails if you were to have functions like this, which we know are impossible. So this is just kind of it's just kind of a sanity test to see that these are two versions of this Bernstein inequality and the first lemma that I wrote down calling the uncertainty principle are sort of the same, expressing the same fact. It's impossible to have a function by the first factor, but have a function like this. There's no such function that's equal to a bump, compactly, its Fourier transform and the function itself are equal or compactly supported bump functions. It's just there's no such function. But just for the sake of argument, you can play with suppose that there were and see what how that would violate this inequality here. How such an example would violate this inequality here. Okay, and let me prove, I can prove Bernstein's inequality for you very quickly. So if we have compactly supported Fourier transform of a function on a ball of radius r, this implies that f is C infinity, right? Because we know that decay properties of the Fourier transform lead to smoothness properties of the function. So f is a C infinity function. We're free to take many derivatives as we like. D alpha of f in L2 by Plancherel, this is equal to d alpha of f hat in L2. And we know that when we take Fourier transform of derivatives, what we get is 2 pi I times xc to the length of alpha times, or to the alpha, times f hat in L2. And we know that since the support of f hat is inside the ball of radius r, this function inside the L2 norm here is 0 if c is in absolute value bigger than capital R. So the biggest this c can be where the function is non-zero is r, right, in length. So this is less than or equal to 2 pi times c, times r to the alpha times f hat in L2. And if we like to put this back in terms of the function itself, this is 2 pi times r to the alpha. It's again by Plancherel. So there's just two applications of Plancherel and the fact that the Fourier transform turns derivatives into multiplication, like C. So this is the proof of Bernstein's inequality. And quantitative versions of the uncertainty principle like this, it turns out, have deep applications. In fact, deep applications, I'd say in a few different fields of mathematics, it turns out, versions of quantitative manifestations of the uncertainty principle, like discovering new quantitative manifestations of the uncertainty principle, is actually like an active area of research, as these often lead to in the context of questions like this arise in a couple different fields, like number theory and PDE, dynamics, things like this. It's kind of amazing how simple inequalities like this turn up in mathematics. Okay, so so this is just a flavor of the uncertainty principle, and you see it's the arguments themselves. We've already done a lot of work. They're not so hard to deduce these types of inequalities. But one other thing one other application I wanted to show you guys of the Fourier transform is some applications to PDE. So maybe start, so applications to PDE. And staying in the same sort of direction, a canonical PDE is the Schrodinger equation. So IDT psi plus Laplacian of psi is equal to 0, and I give myself initial condition psi at time 0 x is equal to some given function f. Psi is a function of t and x, where t is a real number and x is the spatial variable, say in Rd. And we can study an equation like this in dimensions d bigger than or equal to 1. And here, so what's the Laplacian? The Laplacian is the sum from j equals 1 to d of dxj squared. So d equals 1, Laplacian equals minus, or sorry, these different sign conventions. Okay, so this is the Schrodinger equation. So the goal is you're given a function f, f of x. Sorry, I should make this function f of x. This is the initial state for the system, and you're looking for a function psi at time t and x, solving this PDE such that at time 0, psi of 0x is equal to f of x. So we'd like to, given and let's say we know what type of function f is. Say we're given a Schwarzschild function. So f is a Schwarzschild function in Rd. So you hand me a Schwarzschild function in Rd, and we're going to try and write down a solution to the Schrodinger equation. Well, one thing to note is, our tactic to solve it is going to be just take Fourier transform of the equation. So tactic, so take Fourier transform. In the x variable. You can also take Fourier transform in t and x, and this leads to something different. But we'll just try and take Fourier transform in the x variable for now. And what do we get? So this leads to I dt of psi hat. So the Fourier transform is psi is a Schwartz function. And so the Fourier transform just going to commute with, well, let's imagine that psi is a Schwartz function. Later we'll see it is. The Fourier transform commutes with dt, txc. And then we take Fourier transform of plus Laplacian, or maybe I should remember a couple steps. I dt psi hat plus Laplacian of psi hat txc is equal to 0. And note that dt of psi hat of txc is equal to dt of psi hat txc. So that I can pull the dt derivative out of the integral. And the Fourier transform of Laplacian of psi. Remember this, now the Laplacian involves space derivatives, so we know that this turns into multiplication by xi, right? And what in fact we get is this is equal to minus 4 pi norm c squared psi hat of xi, t xi. So you can check this. Let me say one more thing, that what type of function we're looking for. We want so psi to be a complex value function, RD to C. There's an I here, so that should give you a tip that psi should be complex valued. Okay, so doing this, we plug this back into the equation. We obtain I dt psi hat txc is equal to 4 pi psi squared psi hat of txc. I can multiply by I on both sides, or divide by I on both sides if you like. So I'm going to put the I on the other side. It becomes minus I. And now this is, and I take Fourier transform of the initial data as well. At time 0, this is equal to f hat of xi. And what has this done for me? Well, I've taken in a PDE, meaning a partial differential equation, the derivatives, both in what I started with, there are derivatives in both t and x variables. And I've turned it into an equation where there's just derivatives in the t variable. So for each fixed xi, this is an ODE in the time variable. And it's a pretty simple ODE. Its solution is just a complex exponential. So I solve ODE and t, and I get psi hat of txc. I get a solution for the Fourier transform of the function I'm looking for. So psi hat of txc, what is this? This is e to the minus 4 pi I t c squared times some constant depending on xi only, and you can check that I now have to use my initial conditions. The constant in xi can only be f hat of xi. So it's just my solution on the Fourier side is just given by the Fourier transform of my initial data times this complex exponential, which involves t and xi. Well, but then I can apply the inversion theorem, the inversion formula. And what do I get? Well, psi of tx, right? I just do a Fourier inversion, is integral over rd e to the 2 pi I x dot xi e to the minus 4 pi I t. So I'm just plugging in psi hat here. Txc squared f hat of xi dc. And you can check this solves this satisfies I dt psi plus the Laplacian of psi is equal to 0, and it satisfies psi is f of x, which you can, so as long as f is a Schwartz function. So this last equality of the initial data, you need some regularity properties of f to make sure that you can take the limit as t goes to 0 inside the interval, and use dominated convergence, for example. Okay. So, all right, so some observations. About the solution I gave you. So this is nice, right? I just can write down a solution to the Schrodinger equation just by taking the Fourier transform, solving an ODE. Okay, well, the next thing you want to say is, well, what does, if you give me this initial data, what does the solution that I wrote down look like? And it's hard maybe just to look at this formula that I wrote down and notice anything helpful about the solution. Because, well, on the one hand, you have to take a look at the initial data. I need to understand what the Fourier transform initial data looks like as a function. And then I need to multiply it by this complicated looking expression, these complex exponentials, and then integrate it in C. And only then do I recover, I see what my solution looks like. So it's hard just to stare at this formula and see what the solution looks like, which is presumably what I'm interested in. Right? This is a physical equation. The Schrodinger equation arises in quantum mechanics. But we can start making some observations. Okay, well, although it's a complicated looking expression, we can try and unwind it a bit. One thing we can do is just just write out the formula for the Fourier transform, recover, get f in the formula. Right now we still have the Fourier transform of f, so we'll do that in a second. But even before that, I can see that this conserves mass. So the solution conserves the L2 mass of the data, i.e. the L2 norm of psi at time c in L2 is equal to the L2 norm of f, initial data. This is called conservation of mass. How do I see this? The proof. Well, I can try to use this formula that I had, but I could also go back a step and remember the Plancherel theorem, and I know that I have this formula for the Fourier transform of psi. So psi of t in L2, this is equal to, by Plancherel, psi hat of t in L2, which is equal to e to the minus 4 pi I t norm c squared f hat of L2, which is just f times something of a complex vector of length 1, right? This is e to the real number times I. So this is just equal to f hat. Well, maybe I'll write this on the next page. This is equal to f hat in L2, which again by Plancherel is equal to f in L2. So that's the conservation of mass for the Schrodinger equation. The solution has the same, the L2 norm of the solution doesn't change. All right. But okay, I'm still interested in what the solution looks like. And I claim it's not too hard to go from here to see dispersive features of the solution. Dispersive features. So meaning that if I think of this as being, of the solution as being a wave, as time goes on, the size of the amplitude of the wave is going to go down. So the solution is going to spread out its mass and energy, in fact, spread out its mass and energy. And by spreading out its mass and energy, it's going to have to, but still maintaining, so it has, the mass and energy are conserved, but at the same time, they're spreading out in space. The mass and energy is spreading out in space, so the amplitude of the wave is going to have to go down. And so I'm going to prove the pointwise dispersive estimate for the Schrodinger equation. Pointwise dispersive estimate. So psi t as above satisfies its L infinity norm in RD. So just the size of the absolute value of psi is less than or equal to some constant, which depends on the dimension only, times t to the minus d over 2 times the L1 norm of f. RD. So if I have a Schwartz function as my initial data, then the Schwartz function will have some L1 mass. So this is just some constant that's fixed by the, once I pick my initial data, that it's a constant that's explicit, the L1 norm of f. But then as time goes on, I get this factor of t to the minus d over 2 in front. So as t goes to infinity, the L infinity norm of psi goes to 0. And it decays at a specific rate. It decays like t to the minus d over 2. It turns out this is in fact like the a sharp rate as well. So we can't do better than this. So let's sketch the proof. So sketch of the proof. Sketch of the proof because I'm going to skip a step involving some complex analysis. Another advertisement for taking a complex analysis class at some point. Okay, let's do the proof for d equals 1. And remember that I have f hat, so psi hat of tc is equal to e to the minus 4 pi I t times norm c squared, or just c squared in this case. C squared times f hat of psi. Okay, and then I apply the, I'm rewriting a formula that I had above, but just in d equals 1. So tx, so sorry, psi of tx is given by the inversion formula, just the integral over r times e to the 2 pi I x c e to the minus 4 pi I t c squared f hat of c dc. So by the dominated convergence theorem, for each fixed t, I can express this as a limit as delta goes to 0. I'm going to insert a factor in to make this, to complete a square. So what I'm going to do is I'm going to try and complete a square here. So I have an expression involving x and c and t and c. I'm going to try and complete the square. So this is the limit as delta goes to 0, integral over r of e to the 2 pi I x c. Hopefully I have this right in my notes. E to the minus 4, I forgot to square with the pi here. 4 pi squared I t c squared, e to the minus, this is the new factor I'm putting in here, e to the minus 4 pi squared t times, no I now, delta times c squared. F hat of c. 4 type t, okay. I'll do this wrong every time I do it. So hopefully I got it right in my notes. This is the limit as delta goes to 0. Now next what I'm going to do is I'm going to undo the Fourier transform on f. Limit as delta goes to 0, integral over r, e to the so f of y times integral over r. So I just did the Fourier transform of f, e to the 2 pi I have x minus y here times c, since I did Fourier transform on f, e to the minus 4 pi squared I t c squared e to the minus 4 pi squared t delta c squared dc dy. So I've just created a double integral now. And this is equal to the limit as delta goes to 0, f, and I see what I have here is a convolution. Sorry, I have a function. I have a function. I have a family of functions that depend on t delta, but in the it's a function of x minus y. So this is f convolved with a family of kernels with two indices, k t delta of x, where k t delta of x is equal to integral over r e to the 2 pi I x c e to the, and here's where I complete the square, e to the minus pi times 4 pi t delta plus I c squared dc. Okay. So note this is a, okay. So now define, so this is a little technical, but if you bear with me, this is all stuff that we've been doing a bunch. Now define g of t delta of c to be this factor, e to the minus pi times 4 pi t delta plus I c squared. And note that k t delta of x is just equal to the inversion formula applied to this function g. So I'm going to write this as script f inverse. So Fourier, I'm doing Fourier inversion. So inverse Fourier transform of g t delta x. Okay, and then two facts. So I'm just going to try and take this Fourier transform. Recall one, in both, in fact, we can prove using complex analysis. One, we've proved already that the Fourier inversion of the Gaussian function is just, I just recover the Gaussian function back again, right? And then, and note that this is, I've suggestively written this as e to the minus pi times some factor times c squared. So I've expressed this as a Gaussian function with some weight here. And then two is that how the Fourier transform behaves with scaling. If g delta of psi is equal to g of, lambda times psi is, g lambda of psi is equal to g of lambda times psi, then f inverse of inverse Fourier transform g delta of x is equal to, g lambda, 1 over lambda, f inverse of g times x over lambda. So this is just how the Fourier transform behaves with a function that you've rescaled by lambda. Okay, so we want to apply this, apply 1 and 2 with lambda is equal to square root of 4 pi delta plus I times t, which is the factor appearing here. So this, I'm writing this as e to the minus lambda times c squared, then gt. So with this lambda like this, then g delta of c is equal to e to the minus pi lambda times c squared. Right? One problem. So issue is we proved 2 with lambda a positive real number, right? And here lambda, this lambda that we have appearing here is a complex number, right? There's an I appearing here. Okay, but you can do that. So you can recover same formula. Can recover same formula using contour integration. In complex analysis. So line integral over, you express the thing you want, a line integral over the curve x plus I times 0 and c. And then do a change of variables and use the Cauchy integral formula. And you can recover the same formula too, even if lambda is a complex number. Okay, so I'm not going to do that now. You just have to believe me that such a formula still holds with complex numbers as the scaling factors. But what this tells me, so hence, if I take Fourier transform kt delta, I can find, I know what kt delta of x is. This is just equal to 1 over square root of 4 pi t delta plus I e to the minus pi x squared divided by 4 pi t delta plus I. I just use the fact that f, this function f here, or this function g, gt delta is a rescaled Gaussian function, and k is the Fourier transform, the inverse Fourier transform of this rescaled Gaussian function. Apply 1 and 2, and here I have a formula for k, this kernel. So, and then the limit as delta goes to 0 of kt delta of x is just equal to 1 over square root of 4 pi ti, 4 pi it. Let me write I last. 4 pi it times e to the I get the pi's cancel. What do I get? E to the I times x squared over 4t. Let's see. Yeah. E to the I x squared over 4t. And so hence psi of tx equals the limit as t goes to 0 of f convolve with k t delta of x which is equal to, and since f is a Schwartz function, I can pass the limit through the integral, limit as delta goes to 0 of this, which is integral over r 1 over, so maybe I should write this like this, 1 over square root of 4 pi it integral over r times f of y times e to the I x minus y squared over 4t dy. So now I took this complicated looking formula. So what I did here was took this complicated expression for the solution of the Schrodinger equation involving Fourier transform of f and etc. Took the Fourier transform off of f and obtained this much simpler looking expression. And from here, it's immediate that psi is less than or equal in L infinity. Is less than or equal to square root of t to the minus 1/2. So t to the minus 1/2, right? I have 1 over square root of t times the L1 norm of f. Because I can just put absolute values inside the integral, and this factor just has norm 1. And this is the classical dispersive estimate for the Schrodinger equation. Is it possible to sync the file? Sorry about that. I didn't see this. Okay, the file should be syncing now. Okay, any questions on that? I realize that the proof is quite technical. But that's sort of, well, we introduce this trick of introducing this limit as delta goes to 0 in order to complete a square. But that's sort of the only trick that we used. The rest was just brute computation, actually. So that's the Schrodinger equation. It's the dispersive estimate of the Schrodinger equation. One can go much farther from here.
Is this also in Stein book?
Is this in the Stein book? I don't think so. I don't think so. Yeah, I think in the first Stein book, the one on Fourier analysis, there's a chapter about the wave equation. And I don't think the Schrodinger equation is covered. One thing that it wouldn't be in the Stein books until the later ones, and I'm not sure if it is, because there's some complex, like for example, there's some complex analysis involved in this. So one of the Stein books develops complex analysis, and this would be done after that, if it were done at all. But this is.
Thank you very much.
Yeah. But this is in a lot of PDE books, but typically more advanced ones, or more specific ones about, say, dispersive PDE. Okay, so that's the Schrodinger equation, or that's a brief introduction to the Schrodinger equation. Oops, let me try and. Any other questions about this?
Is this equation similar to heat equation?
So no. So yes and no. So let me go back here. So what would be the difference with the heat equation would be if I erase this I, right? Or made this I equals -1 rather. Then we'd have the heat equation. But the heat equation has so it's a fundamental different property. So while the solution to the Schrodinger equation decays in time, the mass is still conserved. Where did I write the mass conservation? So it turns out mass and energy are both conserved. Whereas for the heat equation, if I start off with a nice smooth initial data for the heat equation, heat dissipates. So in fact, the everything about the solution will tend to, if I just start off with the free heat equation like this and let time go, the solution itself will in fact converge to zero. In fact, the L2 norm of the solution will converge to zero. Here the solution decays in L infinity, right, but not in L2, right? So this is a fundamental difference with the behavior of the solutions. So these solutions oscillate in time, right? You can see this from the formula. There's some time oscillation, right? As time goes, this factor changes. And how is this dispersion happening? Well, this is called, what's happening here is called dispersion rather than dissipation. And what's happening is that the frequencies are all moving at different speeds and directions, right? So so you see if I just look at pieces of the initial data, say with frequency, so as you think about how this spreads around in the complex plane, with frequencies localized to some region, then I see the direction of this thing moving is has a c squared here, right? So different frequencies propagate at different speeds. And so the solution kind of spreads out by this phenomenon called dispersion, which is different frequencies propagating at different speeds. Whereas for the heat equation actually just relaxes down to convert, the free heat equation will relax down to zero. So these in fact are quite different. And it turns out that, well, they're quite different, but there's always kind of deep relations between things in math if you're doing things right. And some phenomena you see for in heat type equations, you also see in Schrodinger type equations or wave type equations as well. But they typically, when you start out like studying PDE, these lie in completely different categories because the heat equation has this dissipative property where the Schrodinger equation has this dispersive property. And these are just quite different. These guys oscillate in time forever, right? But whereas the solution to the heat equation just kind of relaxes down to zero, sort of in every sense of the word. In every sense. Does that answer your question?
Yeah, but it is very interesting that only change in I such a different thing.
Yes.
Interesting description.
Yeah. Go. Sorry, I interrupted you.
Yeah, it is a very interesting phenomena. I would expect normally from the beginning like exact similar things, but it is very interesting.
Yeah, multiplication by this little twist, as one of my colleagues like to say, does quite a lot of work. So yeah, there's qualitatively much different properties, and so in many senses, the Schrodinger equation lies sort of in the same, more similar in phenomena to wave equations. Or the wave equation, which I'll discuss briefly next. So the wave equation takes the following form. So I take two time derivatives of u minus Laplacian of u is equal to 0, and u at time t equals 0 is f, and u dt of u. So this is second order in time. So I have two initial conditions: initial position, initial velocity. Dt of u at time 0 this is all backwards. Time 0 it should be 0x f of x. 0x is g of x. This is the initial. You should think of g as the initial velocity, and f is the initial position of the wave. So we started off the class studying the wave equation on a vibrating string, but here we have the wave equation in RD. So t again is in R, x in RD, and u is a function of t and x. Okay. Let's see. There we go. Okay, so this is the wave equation is another fundamental equation of physics, as we saw in the beginning of class. We started with the model of a vibrating string, but then Maxwell came along and the wave equation kind of ceased being a model and started describing just being the description of a true description of physics. So this is electromagnetic waves propagating in a vacuum. So nonlinear versions of the wave equation, if I don't have zero here but have some interaction, so some nonlinear function of u, these arise as classical field theories and in fact in general relativity. So this is kind of ubiquitous. Wave equation, like the Schrodinger equation, are both kind of ubiquitous in nature. And again, you can solve this, just a simple version of the wave equation you can solve by taking Fourier transform. So dt squared of u hat is equal to minus 4 pi in the same fashion, minus 4 pi squared times c squared u hat of times u hat. And so this is now a second order ODE, which we can solve. And the general solution, I'll spare us the computation, but we saw this in the beginning of class. This should be cosines and sines, right? Which is no surprise given this is the solution of the wave equation. So u hat t xc is given by some function a of xc times cosine 2 pi ct plus b of xc times sine 2 pi absolute ct, where a and b we can now determine the initial conditions. So u hat t0 is equal to f hat of xc. This means this implies that a of xc is equal to f hat of xc just by plugging in t equals 0 in this formula. By plugging t equals 0, this sine term vanishes, and I'm just left with, on the left I have f hat, on the right I have a of xc. And if I take dt of u hat and then plug in, I keep doing this. So this is 0 x 0 xc. This is equal to g hat of xc on one hand. This is and on the other hand, this is equal to b of xc times 2 pi times xc. So b of xc is equal to g hat of xc divided by 2 pi times xc. And we're led to the solution, the Fourier transform of the solution of the wave equation, u hat t xc is equal to cosine t 2 pi times f hat of xc plus sine 2 pi t xc divided by 2 pi xc times g hat of xc. So if f and g are both Schwartz functions, say this is the solution to the wave equation, and we can, in fact, if you like, write it out, write out the do inverse Fourier transform. So this is equal to integral over r d of e to the minus 2 pi I so sorry, this is u. The solution itself, u of tx is this, dxc plus integral over rd e to the 2 pi I x dot c sine 2 pi txc divided by 2 pi c g hat of c dxc. So this is the solution to the wave equation. And a more so one can do a couple of things. So analogously to the Schrödinger equation, the wave equation, there's some conservation properties of the solution. So mass is not conserved, but energy is conserved. Conservation of energy is that if I define the energy of u dt of u at time t to be equal to the integral 1/2 the integral for rd, the gradient squared of u plus the dt of u tx squared dx, then it turns out that this is equal to the energy of the initial conditions. So conservation of energy. One way of proving this is via the Plancherel theorem. Again, just like before, it's a little bit trickier. But the same type of trick works. You can prove the conservation of energy via Plancherel. On the one hand, and this equation is also dispersive. In fact, there's so if f and g are two Schwartz functions, then there's a dispersive estimate for solutions of the wave equation. So as time goes on, the energy of the wave is out, but is conserved, so the wave has no choice but to decay in amplitude as well. So the energy, the L infinity norm of u is less than or equal to some constants which depend on f and g in a bit more complicated way. So t to the minus d minus 1 over 2. So the decay rate is a little bit slower for the wave equation. So for Schrödinger equation, we had minus d over 2. For wave equation, we have d minus 1 over 2. So the constant depends on f and g here, the norms of f and g. In fact, I think this is the estimate. So two derivatives of f and L1 plus a derivative of g and L1. So this is in fact quite a bit more involved to prove this. In non-COVID years, I've gotten to this theorem at the end of this class, but we need probably 2 more lectures to do the proof. So it's not as easy as the proof I just gave, was computation I gave for the Schrödinger equation to prove this dispersive estimate for the wave equation. So in fact the proof that I like, there's a couple different proofs. Usually it's called the method of stationary phase. Which is again, it's a little bit more advanced than what's in the Stein-Shikarchi books. So this isn't quite covered there. But it amounts to a careful study of this Fourier representation of the solution. Where are we here? This Fourier representation of the solution. And so where do you get decay in t from this formula? Well, these cosine and sines, this is one way of writing cosine, right, is 1/2 e to the 2 pi I t c. right? Plus e to the minus 2 pi I t c. And then, so combining here, you get the phase e to the, one of the factors, say, is e to the 2 pi I t c minus x dot c. Right, if I combine, say, this factor here with this factor here. And then what you'd like to do, so if I want to get, so my goal is to show that u decays in time. And I see the only place where time t appears is in an exponent, this complex exponent here. And if f is a nice smooth function, or if f hat's a nice smooth function, I think to myself, well, maybe I should try integrating by parts, right? Because if I integrate by parts, if I can write this as the derivative of a function, then I get a factor of 1 over t times c minus x dot c, right? Comes down. So this is equal to d by, so it's a little complicated, but maybe not try to squeeze it in here. Is this making sense at all? So I see, as a complex exponential, I know that I can write those as derivatives of things. I think of it as a function of c. I like to integrate by parts in c. So I can write this as a derivative of something. Well, I run into problems so I can create 1 over t's by integrating by parts, but I don't get just 1 over t. I get 1 over t times norms c minus x dot c. And I'd have problems integrating by parts if that is 0, right? So this is called the phase function here, and the method of stationary phase is a way to integrate by parts even when this has derivative which is equal to 0. This thing has derivative which is equal to 0. Rather, you integrate by parts where you can, and you do something else where you can't. The station is called so-called stationary phase estimate. So that's sort of an advanced topic, but it leads to it's an advanced Fourier analysis topic, but it leads to this dispersive estimate for solutions to the wave equation. So wave decay is like Schrodinger, but with I lose one power. And you can check this estimate is consistent with what we did in the very beginning of class when we studied the wave equation when d equals 1. We saw that the solution to a wave equation on the line is just like you take the initial, if I take, say, data like f comma 0, which if initial velocity is 0, it's just a bump that travels to the left and to the right. So it doesn't decay in amplitude when d equals 1, which you see here. There's no decay in amplitude of the wave when d equals 1, but you see decay. You see this dispersion in higher dimensions 2 and higher. And this phenomena is exactly what you see. Say I'm in dimension 3, I see I have decay like 1 over t. And in dimension 3, the example you can keep in mind is, say, if you take a flashlight and shine the light against the wall. So this is like the electromagnetism, the light behaves like waves. Shine a light stand up close to the wall, and you see a bright circle of light against the wall. And if you stand back, if you move back farther away from the wall, so more time elapses before the light starts hitting the wall, bouncing back to you, I guess. And the size of the disk of light in the wall gets bigger, right? But also gets fainter. So the wave is spreading out, right? So the size of the circle of the disk on the wall gets bigger, but it gets fainter. So I mean, the amplitudes of waves are smaller. So that's a reflection of this dispersive property of waves, and that you see in nature, for example, as light disperses when you shine a light that disperses. Let's see. I think anything else I do details wise will get rushed in the last 10 minutes. So maybe I'll stop here. If you guys have any last questions, I'd be happy to chat for a bit.
Is there Is there any sort of intuition we can draw about which different quantities are conserved with these different differential equations?
Whew, so no. I'd say no, in that meaning search for like type of conservation properties or almost conservation properties is like a ongoing active research field, I guess. In fact, okay, so let me back up a second. So on the one hand, so let's go back to the wave equation. So one different formulation for the wave equation. So let me give a yes, and then I'll give a first, and then I'll give a no. So I'll tell you the ones we can guess. So one formulation of the wave equation is the solutions to this PDE are critical points of what's called a Lagrangian action. If you've taken a physics class or physics classes, I actually didn't take many physics classes, so I don't know, but I know that Lagrangians are kind of sacrosanct in physics, or action functional is sort of sacrosanct. And if you have a Lagrangian, so this is the Lagrangian for the wave equation. So it's a functional, meaning the inputs are functions, and the outputs are numbers, minus dtu squared plus gradient of u squared. So it just looks like the energy functional that I wrote down before, but I put a minus in front of this norm dtu dx, and this is an integral over space and time. So r cross rd. So it turns out that these two are related to each other. So critical points. So if a function has a critical point, if its derivative vanishes, remember from calculus, so functions with critical points have vanishing derivative. So a functional you can think of as having a vanishing derivative as well. It's a bit fancier of a derivative because you have to sort of differentiate, and by moving function, you have to consider what's called variations of the function. It's a bit more complicated, but in practice it looks almost exactly the same. It's just trying to take a derivative of this functional. Critical points of L are solutions to star. The critical points of this Lagrangian action are the solutions of star are the critical points of this Lagrangian action. So you can go back and forth. You can formulate the wave equation as finding the critical points of this Lagrangian action. And there's this famous theorem. It's a beautiful theorem from a physicist called Noether's theorem. By Emmy Noether, who's a famous mathematician, physicist. I'm not sure what to call her, but brilliant scientist. This is perhaps maybe the most underrated theorem in physics, which says that symmetries, so it's almost like a principle, but it's in fact a rigorous theorem. So symmetries of L correspond to conservation laws for a star. So and in fact you can so this is maybe a really rough formulation of Noether's theorem, but you can so I have to be precise about what I mean here. But so one thing, let me just tell you, so that the time translation symmetry here for L, so this is if I take u and if I take a function, if I have a critical point and I translate it in time, I still get another this functional this leaves invariant. It doesn't change the number that this functional spits out if I take the function and precompose with time translation. So time translation should correspond to a conservation law, and the conservation law it corresponds to is conservation of energy. Then space translation corresponds. This is also invariant under space translation. In fact, it's invariant under all the rigid translations of space-time. And so space translation corresponds to conservation of momentum. And then there's another translation, a kind of fancier one. So there's this mixed space and time translation that leaves R cross RD invariant. where I want to think of this as truly a space-time and in special relativity sense. So in the sense of Einstein's special relativity space-time symmetry, they're called Lorentz boosts. So it's a mixed version of space and time translation, and so that leads to what's called Lorentz symmetry of these solutions to the wave equation are invariant under these Lorentz boosts. So any of the symmetries of L give rise to a conservation law. So if you can take your PDE and formulate it as a Lagrangian, in this Lagrangian sense, then from Noether's theorem, you're going to be able to read off conservation laws. So this is an incredibly deep theorem. So one caveat is that not all the PDs you want to study admit such formulations, but then you might say, well, if I'm doing physics, then the ones I really care about should arise from a Lagrangian action, which is like the world that I like to stick in when I do PDs, but people have different tastes. So I like this world where I like study critical points of Lagrangian and things like this.
When you talk about like critical points of the Lagrangian, this is like calculus of variations sort of stuff?
Yeah, exactly. Calculus of variations. Exactly. Yeah.
I touched on it a little bit before, but
yeah. So that's how you find, say, like that's how you're finding like length minimizing curves and things like this between 2 points. The same sort of questions that you asked study those type of questions are exactly how you find critical points of this functional too. So what you do is you consider, so if U is a critical point, then you consider functions U plus epsilon phi, where phi is, say, a smooth, compactly supported nice function. And then I look at L of this, and then I take L, if U were a critical point, then D by D epsilon of this evaluated at epsilon equals 0 would be equal to 0. So where epsilon's a real number. So that's what the variational derivative of this thing looks like. I just kind of put it into a framework where I know how to take a derivative. Right, if epsilon is equal to 0, then I just have U. So I take derivative, and then afterwards evaluate epsilon equals 0. If you do this computation, what you get, and this should hold for every phi, for every, say, phi compactly supported or something like that. If something like this holds for every phi, then you read out that the U has to satisfy this equation.
I see.
So that's how you derive the wave equation from a Lagrangian action. And so in fact this will give you all the conservation laws for the PDE in this sense. But then there's like things like something that's almost conserved, or stuff like that, and that's a bit hard. That's a bit harder. You might have something that's not quite conserved, but maybe grows slowly, or something that grows slower than expected, some quantity that grows slower than expected, and that's more of just like, and when they told you that, like when you're learning integration theory, it's kind of an art form to sort of do a U substitution or something like that. It turns out that trying to find almost conservation laws is a bit of an art form like that. There's no real science to it. Anyway, but yeah, for the wave equation, it has beautiful structure, and there's Noether's theorem, which is an incredible physics theorem. Yeah, my favorite physics theorem, I'd say.
Thanks.
Any other questions?
In field theory, as far as I remember, they were formulating an action from this from some Lagrangian density.
Yeah.
They were saying then they were defining something like e to the I s, which is the action. So in this case, they don't discard necessarily the critical points. They preserve other solutions too, right? If it is the case, how these other points, apart from critical things?
how do those, I see. So how do other objects other than critical points factor into the
PDU? Yeah.
Yeah. So here, and this is a classical field theory, the way and here really the only okay, so here the only things that matter really are the critical points. For different PDEs, so one thing that's tricky about this setting to have this discussion is that this thing doesn't have a sign. This isn't positive definite. So the critical points aren't minimizers or things like that. They're just critical points. So in the case where you have where you're studying, you have an action and you're studying minimizer, you have the critical points are minimizers, then the kind of near minimizers and things like this kind of enter. But in the study of the wave equation, really only the critical points factor. It's kind of hard to see what else is going on just from this action. Or what non-critical points give you from this action. Yeah, so I don't think I could give a good answer to your question. I don't.
Thank you very much.
Yeah.
And for the other part, you said there was some correspondence also between heat equation and Schrödinger equation. In the the solution part, do they just differ in also in just T to I tau? Change of
yeah. So there's a formal correspondence, right? Just changing T to I tau, right?
Yeah.
And this gives a formal correspondence. It's not quite clear to me what's this is a matter of like things, but I haven't in my type of work I haven't seen much use for this formal correspondence. But what ends up happening more like is that there's sort of qualitative properties of bad. So once you so the study of the free equation, when I put 0 on the right hand side, they're very, very different. But if I have some but if instead of putting 0 I have some nonlinear function of f u and du, etc. here. So if I have nonlinear versions of these, would actually come up in these classical field theories. And same for Schrödinger equation. And there are solutions, kind of atypical solutions, sometimes have similar qualitative features for the Schrödinger equation or for the heat equation, nonlinear heat equation, nonlinear wave equation. There are some qualitative, sometimes funny solutions have qualitatively similar behaviors. Maybe let me leave it at that. But so it turns out that studying the heat equation has been a bit easier historically. And so one of the guiding principles about what type of theorems you want to prove about solutions to nonlinear Schrödinger equations or nonlinear wave equations has been what type of theorems one can prove about nonlinear heat equations and see if something qualitatively similar ends up happening for special solutions. Ones where, say, if you have some nonlinear function here, just like an ODE, the solution can cease to exist in finite time, so you can have a singularity or something like that. So studies of singularities, there can be analogies and things like that. But yeah, the formal analogy, just replacing T with I tau, it can be quite challenging, I think, to make this to deduce things rigorously from there. Although it might be useful, it's useful. Formal things are useful, but it's hard to, I think, make rigorous sense of stuff. Yeah, let me leave it there.
I mean, is it possible to scroll up a bit up to the last line of the Schrödinger? No, scroll down a bit up to the the solution part.
Up here. Here.
So if we want solve the heat equation, can we blindly follow?
Yes. Sorry. Yes. You can follow this, and in fact you see that the heat equation is just going to be convolution with the solution of the heat equation will be convolution with a Gaussian kernel.
So the same formula.
The same type of formula, just erase the i's.
So even the solution is in exactly the same way. Again, we can just shift from
with
top.
no I, But these two functions behave very differently, right?
Yeah.
With an I there, this always has norm 1, whereas the other one tends to 0, right? As t.
I mean, in terms of description, yeah, but analytically, we can benefit.
Yeah. Yes. So the answer to your question is, of course, as you like, both yes and no. So yes, it's like formally analogous, and you can follow the same type of procedures for writing down the solution, for example. But then the qualitative properties of the solution itself are quite different because of the differences between the two types of exponentials.
And when we take the integral, since this is this will enter the complex integral, then
yeah.
Once we solve the integral part, the ultimate analytic form, does it still preserve this symmetric formulation, tau to I tau?
Once we go down to this representation of the solution,
you just write the solution in terms of this integral. But if you also evaluate this integral,
the kernel for the heat equation, you just erase the I.
Yeah, exactly. Yeah,
just erase the I. Yes.
Exactly. So once we even solve
yeah.
Still, there is this correspondence.
It still is a corresponds. Yep. Exactly. It's preserved.
This is very strong.
Yeah. But then the thing itself behaves much differently.
Yeah, our observation needs to take account this different description, but underlying mathematical description is like the same.
Yeah.
Tau I tau.
Yeah. Yes.
Now this is very interesting.
Yeah. Well, I spent a lot of my time on these things, so it interests me too. Guys, I have to go to my seminar, so
thank you very much.
I'll stop here.
Thank you.
And thank you for all your help. God bless you and our friends.
Have a good break, everybody.
Thank you so much.
Thank you. Bye.
Thank you.
Finishing up your final assignments. Bye bye.
Thanks.